right, today is day 31, you guys. We're looking at lessons 71 and 72. In the home stretch of the semester, we had to get through lesson 80 and look over that, and that'll be the end of the first semester. So it feels like we've gone through a lot because we have. You guys have done a great job. So let's finish out the year strong. So lesson 71, the only concept we're looking at is parallelograms. And you may say, what's a parallelogram? We've really worked with these before because a square is a parallelogram, a rectangle is a parallelogram. So it's a quadrilateral, has four sides, and both pairs of sides are parallel. So if A and B and DC were to continue on infinitely, those lines would never cross. Same thing with BC and AD. If they continue on infinitely in both directions, they would never cross. So that's what a parallelogram is. In parallelogram ABCD, the measure of angle A is 60. Right? What is C? Well, in a square rectangle, we know they're all 90. In a parallelogram, even when we have two acute angles and two obtuse angles, they still add up to 360. So they're not all 90 degrees, obviously. We're told one is 60. They're still going to add up to 360 degrees. And a rule that we know is our two acute angles, or the angles that are less than 90, are the same measurement, and then our obtuse angles are the same measurement. So if A is 60, C is also 60. And we don't have to go through and use any calculations or anything. We can just remember the rule. Oh, A is 60, C is across from it, so it has to be 60 as well. Well, what's angle? How do we know the obtuse angles? Well, we know this angle plus this angle have to add up to 180. 60 plus 120 equal 180. So B and D, in order for them to be equal, and all four angles to add up to 360, they both have to be 120. 120 plus 120 is 240, plus 60 is 300, plus another 60 is 360. If you have something at home that you can kind of illustrate this with, and you start with a rectangle, and then you pull on the corners, the right, upper right and lower left, and kind of make it skinnier and skinnier. You see that the area is getting smaller and smaller in there. So as these obtuse angles get larger and these acute angles get smaller, these corners are getting closer to each other, so the area is going down. How we find the area of a parallelogram, even if it's a square, rectangle, square, we usually say side times side. Rectangle, we say length times width. A parallelogram, we say base times height. If we call it base and height in a rectangle instead of length and width, we're talking about the same things. It's just in a parallelogram, the height may not necessarily be one of the sides. If it's not all right angles, then it's going to be drawn in. Down the road, we'll figure out how we can find the height when we're not given it, but for right now, you will be given the height. The height has to meet the base perpendicularly at a right angle. So this is not the height, this is the height. And then we just do base times height. And we worked with triangles, which is base times height divided by 2. That's because a triangle is half of a parallelogram. And so if we have example 2, 6, not times 5.2, because this is going up at an angle that is not 90 degrees. So this dashed line out here tells us that this is our height, which makes it nice. We don't have to go and find it. If we were doing perimeter, then we would, this side would be 6, this side would be 6, this other side would be 5.2, and we would just add them all up. But for area, we just do base times height. 6 times 5 is 30, so it's 30 square centimeters. And that's all we do. Just plug, if you know the base and height, plug them in, multiply, and you're done. It's base times height. This practice set we will go over as a class. Lesson 72, we're looking at fraction charts and multiplying 3 fractions. So fractions chart. Again, if you want to remember these steps or this kind of jingle, write the problem in the correct shape, form the operation, and simplify. So SOS, shape, operation, and simplify. That helps you remember. So the shape, what we mean by that, when we're adding or subtracting, you have to have common denominators. For adding or subtracting, fractions, mixed numbers, anything with the fraction, we have to have common denominators. If we're multiplying or dividing, we have to write them in fraction form. So if we're multiplying or dividing a mixed number, we have to rewrite it as an improper fraction, so that way it's in fraction form. Then operate, add or subtract the numerators. If we're multiplying or dividing, we multiply or cancel. If we're dividing, we keep, change, flip. So again, we keep the fraction, change the division to multiplication, and then flip, or making the reciprocal of that fraction. When multiplying, multiply the numerators and the denominators, and then simplify at the very end. And we always want to reduce. But then on a lot of tests, when you guys leave something as 2/4 instead of reducing it down to 1/2, for example. So again, I think this is kind of wordy and it may help you, but it's just what we've been talking about already. We need common denominators. When we're multiplying, we just multiply numerators and denominators. When we're dividing, we keep, change, flip, and we always reduce. So that's all this is doing. It's just putting it into a chart to maybe help you kind of memorize or categorize what's going on when we do that. When we're multiplying 3 or more fractions, we follow the same steps. So if we're adding or subtracting multiple fractions or mixed numbers, these rules still apply. When we're multiplying or dividing, the rules still apply. So if we have this one, 2/3 times 1 3/5. Times 3/4. They're all multiplication, but we first need to convert this one. This is a fraction, this is a fraction. Those are both good. This we need to get in an improper fraction. So how we do that, we think of this as 5/5 plus 3/5, which is 8/5, or we do the whole number times the denominator, which is 5, plus the numerator, which is 8/5. So this one's going to become 8/5. Now we can multiply it all out and then simplify, or we can look for anything that we can factor in any of the numerators and any of the denominators. So what do we mean by that? 2/3 we can't reduce, 8/5, 3/4 can't reduce. But if I look, there's a 2 up here and a 4 down here. Okay, they have common factors, so 2 goes into both of those. 3 down here, 1, 8, 3. Oh, 3 up here, so 3 and 3 would cancel out. 3 goes in both those one time. 8 and 5. Oh, well, I have 2 still down here and 8 up here, so 2 goes into 8 4 times, and so 2 once. So again, I like to do this method just so that way the multiplication, 1 times 4 times 1, is much easier, and the simplification is a lot easier. We could do 2 times 8 times 3 over 3 times 5 times 4, and then reduce. It just feels like a little bit more work. If we can reduce when they're smaller numbers versus when they're bigger numbers, that's going to multiplication is going to be easier, and then it, more than likely, unless we miss something along the way, it's going to be reduced as far as it can be. So 1 times 4 times 1 over 1 times 5 times 1, so 4 over 5. And the same rules apply. There was 3 fractions instead of just 2, which we've been working with, but it didn't change anything. So it looks like that is your only example. So we'll do that practice set together when we get to class. Lesson 73 and 74 we'll be doing in the next video. So that's all we have for this one. Thanks.